All right. Hi, everyone, and thank you for joining us today. We are very lucky to have Abel Lacabanne from UC Louvain today, who's going to tell us about Fourier matrices for GD1N via quantum general linear groups. So please, Abel, take it away.
Okay, so thank you. Thank you for giving me this opportunity to explain my work. So as the title says, I will talk about the Fourier matrices for GD1N and explain how we can obtain them from representation theory of quantum general linear group. So here's the outline of my talk. So the first three parts will be the first part of the talk, so the 35 first minutes. And the fourth part will be the last 20 minutes. So I want first to explain the decategorified story. So what I want to categorify. So this will be a notion called base rings and modular data. And then explain how we can categorify these things. So using modular category and slightly degenerate categories. And why do I want to talk about this thing? It's because these modular data arise in representation theory of finite group of Lie type and in generalization to complex reflection group. So I want to give a short digression on finite group of Lie types. And finally, I will explain exactly what are these Fourier matrices and how do we obtain them from quantum GLN. So first we will start with base rings. So we will look at rings which are free as Z-modules and a finite rank. So this ring have a basis. So we fix the basis of this ring and we define the structure constant of this ring by multiplying two elements of the basis and writing this multiplication as a linear combination with integer coefficients on this basis. So we obtain some integers, which are called the structure constants. And what we are interested in is to find the categorification of this ring. So what does it mean to find the categorification of this ring? That can have many solutions. So we can categorify a ring by different ways. So what we want to find a category such that we can define a quadratic group. So for example, we will have an additive category or an abelian category or even triangulated category. So I will mainly stick with the case of abelian categories. Then we want this quadratic group to be a ring. So how do these translate this property on the category C? We will ask the category to have a monoidal structure, which at the level of the quadratic group will define a multiplication. And then finally, we want to have an isomorphism between the quadratic ring of the category C and the ring we started from. And moreover, this ring has a basis. So we want to have a set of distinguished objects, so which will be often the simple objects or the indecomposable objects of the category. And we want, through this isomorphism, we want these objects to be sent to the basis Bi we started with. And we can add a lot more constraints to the category. So for example, if the ring is commutative, we can ask the category to be braided, because a braided category always have a commutative quadratic ring. Then, for example, if moreover we have an involution on the basis, so this is often part of the definition of base ring that we can find in the literature, that there exists an involution which extends linearly to an anti-involution of the ring. So this involution at the level of the category C will be understood as a duality. So we might ask the category C to have duals. And we can add a lot more constraints on the category C. And next, I will talk about modular datum and explain what are the constraints we will add to the category. So usually, if we start with a ring like this, and this problem is usually hard, it's usually difficult to find a categorification, and it's often not possible. So some rings are not we cannot categorify some rings. So I want to give this example, which is a result of Ostrich. So this is related to the classification of fusion categories of rank 2. So if we start with a base ring of rank 2, so with the unit the unit of the ring and another element, and we will add that the square of this element is equal to 1 plus n times itself. Then we have a categorification of this ring with a fusion category. So I will explain later what is a fusion category, but this is some of the constraints we will put on the category. And there is a categorification if only if n is equal to 0 or n is equal to 1. So very few of this ring admits a categorification with a fusion category. So of course, if we remove the term fusion and ask for another type of category, the answer could be really different. And so now I want to explain where do the base ring I prefer comes from. They come from the notion of modular data. So I just want to say that there are two notions here. So the notion of N-modular datum or a Z-modular datum. So these two notions will be quite the same, but there is a slight difference, which is really huge at the level of the category, at the categorification. So in a modular datum, we will ask to have four things. So first, a finite set. Then we want to have a square matrix indexed by this finite set with value in the complex numbers, then a diagonal matrix, and finally, we want to have some special element in the set I. And now we will add some axioms to this, this notion of modular datum. So first, we want the row. So we want the row of the special element to be non-zero, and much more, we want every element in this row to be non-zero. So maybe some of you have already seen a definition of these things, and here we want to have a positive real number. So here I just want a complex number which is non-zero, so it's quite different. I want the matrix S to be symmetric and unitary. And then I want this condition of the matrices S and T. So in fact, the matrices S and T define a representation of the group F cell 2 of V. And finally, so up to the fourth axiom, we didn't see the difference between an N-modular datum and a Z-modular datum, but here we will see it. So we want that for all I, j, and k in I, this number is either a non-negative integer or simply an integer, depending either we work with an N-modular datum or a Z-modular datum. And so these are the structure constant of a commutative ring, which is called the fusion ring or the fusion algebra of the modular datum. So as before, we have a basis and the multiplication is given by this formula. And the formula defining the integers make this ring to be, for the ring to be commutative and of course associative. And now I want to ask a first question and I will answer it in the second part. And the question is, what does it mean to categorify modular data? Because we want a categorification of the fusion ring or the fusion algebra, of course, but we hope to add some more constraints on the category C to recover both the matrices S and T. So not only we can understand the ring, but we can also understand the matrices S and T. So now we switch to modular categories and slightly degenerate categories. So this will be an answer to this question. So first I start with a lot of constraints I will put on my category. So first I want the category to be C-linear and abelian. So this is a lot of, this is first a thing I want to on my category. So we can work on an algebraic closed field of characteristic 0, but I choose to work with C. It's more or less the same thing. And we suppose that C is a tensor category. So we want this category to be a monoidal. So we will have a tensor product, we will have a unit object, and this tensor product is bilinear homomorphisms. We want this category to be rigid. So we want to have right dual, left dual, so evaluation maps, co-evaluation maps, and so on. So we want duals on the left and the right. And we want some finiteness conditions. So we want the category to be Artinian. So every object will have finite length. We want a finite number of simple objects. And finally, we want that the endomorphism ring of the unit objects is simply C. So it's only the only interesting morphisms are the multiple of the identity. And finally, we want the category to be a fusion category. So to be a fusion category, we add something. We add that the category is semi-simple. So every object is isomorphic to a direct sum of simple objects. So a simple object will have an endomorphism ring isomorphic to C. And so we'll denote by O of C the set of simple objects, of isomorphism classes of simple objects. And now the fusion ring of a modular datum is commutative. So we will ask some more things. So we will ask the category to be braided for the commutativity. And we will ask something which for now may look quite technical, but we want to keep in mind that the one of the biggest class of examples of fusion category are representation of finite groups. So the category of representation of finite group will be a fusion category. And so if you think of a vector space and its bidual are isomorphic and in a way which is canonical. So we want here to have a natural isomorphism between an object and its bidual such that it's compatible with the tensor product. So this is called a pivotal structure. So there is a refinement of this notion of pivotal structure, which is called a spherical structure. So just explain what this is. So when we have a pivotal structure, we have a notion of quantum traces. So what is quantum trace? Let's think we have a map from an endomorphism of an object X, which is not necessarily simple. Then the quantum trace will be some scalar which is associated to this endomorphism. So exactly the same thing as if you have an endomorphism of a vector space, a finite dimensional vector space, you have its trace which does not depend. So if you write a matrix for this endomorphism, the trace does not depend on the choice of basis. So here it's more or less the same thing. You have a quantum trace. And if you take the trace of the identity, you obtain a notion of dimension. And if we have used the braiding and the pivotal structure, we obtain something which is called the twist. So the twist is an endomorphism of an object X, and we have a formula relating the twist on the tensor product of two objects with the double braiding and the tensor product of the twist. So I was talking just before about spherical categories. So the spherical categories is a case when positive and negative quantum traces, so sometimes called left and right quantum traces, there are different terminologies, are equal. So instead of having two quantum traces, we only have one. However, the example I will give in my talk won't be spherical, so I want to keep this notion of two quantum traces, even if I will mainly use only the positive quantum trace. So now that we have a modular category, a category with all of these things, we don't quite have yet a modular category. We will add one more constraint to have a modular category. So we now define what is called the S matrix. So the name is related, of course, of the matrix S in the definition of the modular datum, because we expect this matrix to be more or less the matrix S in the modular datum. So this matrix is indexed by simple objects. And how do we construct this matrix? It's easy. We take the tensor products of these two objects. We take the double braiding. So we braid from X tensor Y to Y tensor X and again to X tensor Y. So we have a morphism from X tensor Y to X tensor right to X tensor Y. So we can take its trace. And this is the entry of the matrix. And if we want this matrix to be part of a modular datum, recall that in the definition of the modular datum, the matrix S satisfied some equation. So S to the fourth power was the identity. So we need this matrix to be invertible. However, it's not always the case. For example, if you start with a category which has a symmetric braiding, of course, this matrix will be always a trace of the identity. So you will have a matrix of rank 1 because f of xy will be the dimension of x times the dimension of y. So we'll call the category to be non-degenerate if this matrix is invertible. And so the category will be modular if it has all the properties listed above. The pivotal structure is spherical, and this matrix is invertible. And there's this theorem of derive, so it dates, I think, from 94, I guess. And if we have an nondegenerate category, so recall that we have a twist, and we will look at the diagonal matrix given by the values of the twist on simple objects. Then this defines an N-modular datum. So here I wrote a tilde on the S because it's not exactly the matrix S, but we need to renormalize it because the fourth power of S is a multiple of the identity. So we need somewhere to renormalize this matrix to obtain something of fourth power is equal to 1. So it's nice, we have an N-modular datum, and moreover, we can really easily understand the fusion ring of this modular datum because it's simply the Grothendieck ring of the category. So this matrix S, so if we go back to this formula, where the matrix S is given by the trace of these double braidings, this formula gives you a multiplicity of an object in the tensor product of two objects. So this formula is often called the Verlinde formula. And so now, what does it mean to categorify a modular datum, an N-modular datum? The answer is, okay, we will try to find a category with a lot of properties such that the modular datum defined by the category is equal to the modular datum with categories. But I want to have a notion of not only the N-modular datum, but I want to have the notion of Z-modular datum. So I want to understand what I need to understand what does it mean to this number to be negative. Because here we understand this number as a multiplicity. So a multiplicity is always a positive integer. So if we have some negative structure constants in our fusion algebra, it means that we should have some sort of negative multiplicities. So there are many ways to understand negative things in a Grothendieck ring. So for example, we can work with triangulated categories, where the suspension adds a sign. But here I want to use the notion of slightly degenerate category, which is related to supercategories. So categories enriched over the super vector spaces. But just before to talk about this slightly degenerate category, I want to go back to this definition of non-degeneracy. So it's quite annoying that to understand this non-degenerate definition from something which is not really internal in terms of the category. So you had to compute a trace and go back to something which is quite decategorify if we want. And so we have a way to understand this non-degeneracy property inside the category using the notion of symmetric center. So an object is a symmetric center if whenever we compute the double braiding with any other object, we obtain the identity. So that's why it's called a symmetric center, because the symmetric center will be a symmetric subcategory of C. And of course, if we have a simple object which is non-trivial in the symmetric center, since this map is the identity, when we compute the trace, we only obtain the dimension, and we obtain that the row of X is a scalar multiple of the row of 1. So this matrix is not invertible, of course. But it is a fact that the category is non-degenerate if and only if the only objects in the symmetric center are isomorphic to direct sums of the unit objects. So we will only have one simple object, so the symmetric center is equivalent to the category of vector spaces. So now we will allow the symmetric center to be slightly bigger, and by allowing this, we will understand some negative structure constants. So what do I mean by slightly bigger? It's just a little bit bigger. So instead of having only one simple object in the symmetric center, I will have two simple objects in the symmetric center, which are not isomorphic. So we will suppose that the symmetric center is equal to the category of vector superspaces, of course, finite dimensional superspaces. So the category C is slightly degenerate. So this is a definition of a slightly degenerate category. So we have in the symmetric center a simple object, which is 1, and we have another object, which I will call epsilon. And this object, if we think of it in terms of superspace, is a one-dimensional purely odd superspace. So of course, its tensor square is isomorphic to the unit object. So now I will put some hypothesis, which is quite important on the dimension of this object. So I will suppose that the positive and negative quantum dimension of epsilon are equal to -1. So we have two choices. Since the unit object is of dimension 1, the square of the dimension of epsilon is equal to 1, so either +1 or either -1. So I want it to be -1, or equivalently, I want the twist of these objects to be 1. So this is really the important condition. Because if we have a category which is degenerate, so which is not non-degenerate, we have a way to force it to be degenerate. So we have a way to construct a non-degenerate category from this degenerate category, but we have some conditions on the twist of the objects on the symmetric center. And this condition is that the twists are equal to 1. So here I want the twist to be equal to 1, to be more or less the same thing, to start from my slightly degenerate category and to obtain a non-degenerate super category. So this is why I have this hypothesis of the twist to be 1. So it looks like it's a technical assumption. And if you take it to be -1, all the theorems I will give after are wrong. So I have counterexamples. This does not usually define the Z-modular datum. So now if we look at the matrices S and T, now they have a block decomposition. Because if you try to compute the S matrix, the row of X tensor epsilon, if you use the definition of the properties of the braiding and so on, you will see that it's up to the dimension of epsilon. So up to -1, it's the row of X. So that's why we have some minus signs. And for the twist, you see it's that the twist of X and the twist of X tensor epsilon are the same because the twist of epsilon is equal to 1.
Can I ask
So now, yes, sorry.
Is it obvious that X tensor epsilon and X are always non-isomorphic?
Just now. So it's not entirely obvious. So here it's easy because I suppose that the dimension of epsilon is -1. So the dimension of epsilon tensor X is minus the dimension of X, and in a fusion category, the dimension of X is non-zero. But if we choose that the dimension of epsilon is equal to 1, it's also true, but it's a different argument. So I think it's proved in the book Tensor Categories of Tingoff, Ostrix, and so on. So here we have, we will look at this tensorization by epsilon on the set of simple objects, so there are no fixed points. So we will choose a system of representative of this action, and we will choose that the unit object is inside it. And now we obtain a Z-modular datum. So how do we obtain it? So we only choose half of the objects. Here's the matrix S. So I should have put a tilde here. So because it's the renormalized S matrix, but we restrict it to the entries of elements of J. So we only took one block of the matrix S. Similar for the matrix T, we take only one block, and for I0, we take the unit object. And this is a Z-modular datum. So the structure constant can be negative. And of course, we understand very well the fusion algebra. So it's not the Grothendieck ring of the category C, but it's a quotient of the Grothendieck ring. And so this quotient more or less says that we want to identify the object epsilon with -1. So we can have a framework in terms of supercategories. And this quotient means that we have an odd isomorphism between epsilon and 1. So having an odd isomorphism will change the sign in the Grothendieck ring. And now the structure constants. So if n of x, y, z are the structure constant in C, and s of Sn are the structure constant in the quotient, we obtain that the structure constant in the quotient are a difference between structure constants. So often, and I think in all the examples I know, either this number or that number is equal to 0. So there is this conjecture that the product of these two numbers is always equal to 0. And in all the examples I know, there is a grading on the category, and epsilon is non-trivial grade. So this will imply that if z appears in X tensor Y, epsilon tensor z won't appear in X tensor Y. So now if I want to categorify a Z-modular datum, I will try to find a slightly degenerate categories with all of these properties and hope that this category has a Z-modular datum equal to the modular datum I started with. And so why am I interested in this? So at first I was interested in the representation theory of finite group of Lie type. And these modular data appear in some generalization, which is called spaces. So I want to explain just some of the motivations. So we will take Q is equal to the power of prime number. And we will take a reductive group over the algebraic closure of Fp, and we will suppose that we have a Frobenius endomorphism on our reductive group. So if you don't know anything on this story of reductive groups and so on, you can think of GLN of F, so the general linear group, and the Frobenius map will be the map which raises every entry of the matrix to its qth power. And so what is interesting is that we have a finite group if we take the fixed points of G under this map. So if we start with GLN, if we take the fixed points under this map, it forces the entry to be in the finite field FQ. And so these groups are quite important because some quotients of them appear in the classification of a finite simple group and are most of the finite simple group. And to understand its representation theory, Deligne and Lusztig defined in 1976 a notion of unipotent characters, so using what is called nowadays Deligne-Lusztig induction. And these unipotent characters, Lusztig explained how to classify these unipotent characters and how to understand the representation theory of the finite group only using unipotent characters of some other subgroups of GF. And in this classification, he uses a tool which was quite important. He partitioned these unipotent characters into families. So if we take the example of GLN, every family is trivial. So every family has only one element. So this won't be really an interesting case from the point of view of modular datum. Something much interesting appear in type B or in type C, for example, or with sp2n. And in fact, to each family, Lusztig associated an N-modular datum. So F is a family, so we have some unipotent characters. S of F is the matrix S of this modular datum, so it's called the Fourier matrix. So this is what I want. What is the name Fourier matrix? Why I have Fourier matrix in the title of my talk. And there is this matrix T, which is a diagonal matrix of eigenvalues of the Frobenius on the unipotent characters. And then we have some special unipotent character. So to each family, we have a modular datum. So question, can we categorify it? The answer is known since Lusztig. So it always comes from a modular category. It's a category of representation of the Drinfeld double of finite group. And quite interestingly, the only finite group which appears in in this story are only the trivial group. We have some power of the cyclic group of order 2. And then we have some symmetric groups, the symmetric groups S3, S4, and S5. And the symmetric groups only appear in exceptional type. So for example, S5 only appear in E8. But it's always a category of representation of the Drinfeld double of finite group. And we have many other ways to think of this modular category. So for example, there is a geometric realization of this category. There is a realization as a center of some category built from Zorgel bimodules and so on. So there are many different ways to think of this category. And there is something quite astonishing in the classification of unipotent characters is that nearly nothing depends on Q. So if you work with GLN of F2 or GLN of F29, the classification of unipotent characters will be the same. You have the same number of unipotent characters. And you have something much stronger, is that every dimension of a unipotent character is a polynomial in Q. So we have some sort of generic behavior of this unipotent character. And there is this observation, which is due to Lusztig, Brouet, Malle, and Michel, is that we should be able to reconstruct everything just using the Weyl group of the reductive group. So we forget the finite field we are working with. And so Weyl groups are rational reflection groups. So the natural question was, can we do the same thing with a Coxeter group? So can we have some combinatorial notion of unipotent characters? Or even better, can we do this with complex reflection groups? So this is a project called Spätzes. So I just want you to give this fun fact of why it's called Spätzes. It's because in 1993, there was a conference in a Greek island, which is called Spätzes. And it was on this island that Brouet, Malle, and Michel first started to compute unipotent characters for complex reflection groups. And so they computed the unipotent characters for the complex reflection group, which is of rank 1 and which is isomorphic to the cyclic group of order 3. And so they decided to call this mysterious object, which should generalize a reductive group, they decided to call it Spätzes, because they were on this island called, in this Greek island called Spätzes. And so soon after this conference, Lusztig understood how to treat the case of Coxeter group of type H3, H4, except for the biggest family, the big family of H4. There is one family he wasn't able to compute, so which is of size 74. So Malle then later computed it using, I guess, Maple or GAP, I'm not sure. So he uses the symmetry that the Fourier matrix should have to understand the case H4. And Lusztig also understands the dihedral group. So he called, for dihedral group, he called the S matrix was called the exotic Fourier transform. And so for Coxeter groups, we always obtain an N-modular datum. And then Malle in 94 treated the case of GD1N and GDDN. So these are two complex reflection groups. So maybe I will just say a few words about this, complex reflection groups. So the classification of irreducible complex reflection groups. So we have one infinite family, so which is indexed by 3 integer. So G, D, E, E, N. So here we have two special cases. When E is equal to 1, so we have G, D, 1N, and here where D is equal to 1, so I renamed E as D, so we have G, D, D, N. So these can be understood as some matrix subgroups of GLN. So so maybe I describe this group in terms of matrices. So you take the n by n square matrices, which are monomial, and each entry is a dth root of unity. So you have a group, and if you take D is equal to 2, here you obtain the Weyl group of type B. Here, if you take D is equal to 2, you obtain the Weyl group of type D. So this could be understood as some generalization to complex reflection groups to the Weyl group of type B and D. And finally, there are some exceptional complex reflection groups. So there are 34 exceptions. And for some of them, we can do this story of constructing unipotent characters and so on. So I will stop here for the first part, and in the second part, we will see exactly what are these Fourier matrices and how to categorify them.
Great. So maybe let's take we would normally take a little break in the middle. So let's take a small 5-minute break. Is that okay with you? Do you still have enough time to finish?
It's okay. It's okay.
Okay, great. So then let's take a small 5-minute break, and everyone can ask them questions if you'd like, or go wander, but come back. So I'll pause the recording for a second.
Okay, so now I'll talk about this Fourier matrix for this complex reflection group GD1N. So the group GD1N, so it's, as I said before, if we take D is equal to 2, we obtain the Weyl group of type B. So GD1N can be understood as a generalization of the type B. And in fact, what Malle did in constructing the unipotent characters, the families of unipotent characters, the Fourier matrices, and so on, he just generalized the combinatorics of symbols in type B. So if you discuss with Malle, he will say that Lusztig did everything, and he just changed the 2 into a D, and everything worked well. So for each family of unipotent characters, we have a Fourier matrix, we have a diagonal matrix of eigenvalues of the Frobenius, and there is a special element such that this 4 tuple is a Z-modular datum. So Malle constructed everything and proved everything except that the structure constants are indeed integers. And Kunz did this, I guess, 10 years later, so he was a student of Malle. And so now the question, so I will answer to it positively, is there a categorification of this data? So to construct the categorification of this data, it's we need to understand really what the matrix, the Fourier matrix is. So we will look at the character table of the cyclic group of order D, and we just renormalized it by a factor square root of D. So this is done just such that the fourth power of S is equal to the identity. And then, so there is a complete combinatorial description of the family F of the Fourier matrix. And what is important here is that this Fourier matrix is defined using a bunch of integers between 1 and D, such that the sum of these integers is equal to 1 modulo D. So this is really important from the categorical point of view, and I'll explain it. I'll explain later why. And this matrix is a scalar multiple. So scalar multiple always just to ensure that the fourth power is equal to 1, and it's a scalar multiple of a submatrix of this matrix. So the submatrix is of index D. So we will take only one row out of D and one column out of D. And so we start with the matrix S, and we take its N1 exterior product, and we do the Kronecker tensor product, and so on. And we take the complex conjugate, so it's not that important. So we have some building block, which is the exterior power of this matrix S. So it's natural to first start to understand this nth exterior power. And then if we have a categorification of the fusion algebra given by this matrix, we will hope that we can mimic the construction of the Fourier matrix with these building blocks. So just a bit of notation, I will write IND, the set of strictly increasing tuples between 0 and D, just so that this matrix has its entries indexed by IND. And then if we want to have a modular datum, we need a special element in IND. So we have several choices. We have a choice for every integer. So for every integer, we take the tuple p, p plus 1, and so on to p plus n minus 1. We reduce it modulo d, and then we reorder it. We order it. And so we obtain an element of IND. And what Kunz showed is that this four tuple, so this set, the exterior power of the nth exterior power of S, and there is a diagonal matrix, so I don't want to talk about this diagonal matrix because it's not the most difficult thing in this, the nth exterior. And this special element, we have a Z-modular datum. So for every choice of P here, so I said that we have a choice for every integer, but if we take P and P plus D, we obtain the same thing. So basically, we only have D choices of unit elements. And not only Kunz showed the theorem, he proposed some conjectures about the fusion algebra. And these conjectures were very precise and made me believe that it was indeed categorified. It was really indeed possible to categorify this using slightly degenerate categories. So the first conjecture, both of the conjectures deal with the fusion ring defined with this exterior power and the unit element. So just a bit of notation. So the structural constant, I will write a P in the bottom left corner. And the first conjecture is that if we take n strictly between 1 and d, there are signs such that if we change the basis using these signs, the structural constant of this ring are non-negative if and only if n and d are not both even. So how did he conjecture this? He did a lot of computation using a computer, and so that indeed he could only find these signs when n and d were not both even. And maybe another conjecture, which was the first one I encountered, is that if we replace the structure constant by their absolute value, we still obtain an associative multiplication. So this can really, we can understand this from the categorified point of view very, very well. So this conjecture made me believe that there is a categorification using a slightly degenerate category. And just to give an example, this behavior is very specific to the ring and to the basis we've chosen, because I took a random example, and if you take a random example, you will have a problem. So for example, I took the representation ring of the group S3, and instead of using the usual basis of the trivial representation, side representation, and two-dimensional representation, I subtracted the unit representation from the two-dimensional representation. And if you compute using the absolute values, you obtain something which is not associative. So this conjecture is quite precise and really is a good sign that we should find a category. We have a good hope to find a categorification. And so now I construct this categorification. So how do we construct it? Using the category of representation of GLN. So the n corresponds indeed of the exterior power we will work with, and the d will appear later when we will replace q by root of unity. So I don't want to give every detail on UQ of GLN and so on, but we only work with the category of representation. So we have the category of finite dimensional weight modules. And this category is a semisimple. So we have a semisimple category. So this is one of the properties we wanted. But this category is way too big, because we will have an infinite number of simple objects. And we only want a finite number. So what is nice with UQGLN is that it has a structure of Hopf algebra. So we have a tensor product on the category of representation. We have a left and right duality. So these were the kind of things we wanted to have. So since I restrict to finite dimensional representations, I will always have all the good properties about Artinian and finite length and so on. And we have also many pivotal structures. So this is something I want to emphasize, that here we have not only usually if you do this construction with S and N, you do not have a lot of pivotal structures. You have a spherical structures, and it's more or less the only thing you have. But here we have a lot of pivotal structure, and this is due to the fact that GLN is a reductive algebra and not a simple algebra. So we have a center, so we can twist the pivotal structure using the center. Another thing which is nice is that we have a notion of R matrix. So it's not exactly an R matrix, it's a quasi-R matrix. It's not only in the tensor product of UQGLN with itself, it's in a completion, but still it gave us a braiding on the category of representation. So we have a braiding, we have a monoidal structure, we have a pivotal structure, and so on. But we have an infinitely many isomorphism classes of simple objects. And we can understand them very well. It's indexed by the set of dominant weights. So it's tuple of integers which are decreasing. So now I want to truncate this category. So this construction is quite classical. So to truncate the category, instead of working where Q is an indeterminate, we will work with a root of unity. And so if you're used to working with quantum groups, usually when we work with roots of unity, the behavior is quite different. So we have different versions of quantum group at roots of unity. The representation theory is much more complicated, but here we will have something quite understandable and quite easy to work with. So we will use the restricted integral form of GLN. So it's some subalgebra of UQ of GLN, and then we can specialize to a root of unity. So here I use a 2D root of unity. So remember that I had a dth root of unity for my matrix S and its exterior power. Here I have a 2D root of unity. And so we have a quantum group. So it's a version of GLN at a root of unity. And it's still a Hopf algebra. And since we use the restricted form, we still have a quasi-R matrix. So if we look at the category of finite dimensional weight modules, so here we have to be a bit careful when we define what a weight is. We obtain a category which has a braiding, because we still have a matrix, which have tensor product, we have pivotal structure and so on, but it's not semi-simple. So by doing this, we completely destroy the semi-simple property of the category of representation. And this category is way too big. So we have way too much simple objects, way too much indecomposable objects, and so on. So we need to restrict to what is called tilting modules. So I don't want to go into details, but we will look at some nice subcategory, nice full subcategory. So using this notion of Weyl modules, so these Weyl modules are specialization of the simple modules. But Weyl modules are not necessarily simple. And a module which is tilting if and only if it's filtered and co-filtered by Weyl modules. And the first thing is that when we take a subcategory, we are not sure that it's closed under the tensor product. And this is a theorem of Anderson, that the tensor product of two tilting modules is a tilting module. And still the same problem, we do not have a semi-simple category, we do not have a finite number of simple objects, and so on. And so now we need to perform some something on our category which is called the semi-simplification. So these work quite well in general when we have a pivotal monoidal category. So some other technical assumptions. So we don't need the category to be finite, the category to be semi-simple. But of course, we don't need the category to be braided and so on. And so when we do this, we transform our category C into a semi-simple category. And it's called a semi-simple simplification of the category. And maybe the most interesting thing from my point of view is that how the simple objects behave in this category. So how can we understand the simple object in the semi-simplification? In fact, there are bijection with indecomposable objects in the category we started with, which are of non-zero quantum dimension. So how do we construct this category? We kill a lot of morphisms. And killing a lot of morphisms, we will kill the morphism which are of trace zero, so we will kill the objects with zero quantum dimensions, the indecomposable object with zero quantum dimension. And so we can start, we may have started with a category which was quite nice with a finite number of simple objects, but with a really big number of indecomposable objects. And so it's usually hard to understand this semi-simplification because you start with a category which has very few simple objects, and then when you semi-simplify, you have something quite huge. So here we will look at the semi-simplification of the full subcategory, of the full subcategory of tilting modules. And here, it's quite well known. So this category, of course, is semi-simple because it's a semi-simplification. Still, we have infinitely many non-isomorphic simple modules, but here we have a classification of the simple modules. So it's more or less the same thing. We have the dominant weights in GLN, but here we have a condition on the difference of lambda 1 minus of the difference between lambda 1 and lambda n. So we want this number to be, it's not too big. So that's why I said earlier that we want to truncate the category. And so now, still I have an infinite number of simple objects, but the symmetric center is quite big. And so if we want to have a non-degenerate category or a modular datum, we want to kill the symmetric center. So the thing is to understand, is now to understand the symmetric center. So the symmetric center is tensor generated only by one object, which has a quantum dimension which depends on n and d. So I said earlier that we have many pivotal structures. So I need to make a choice of pivotal structure. So for every p, so for every unit object I want in my base string, I have chosen in a clever way some pivotal structure. And the quantum dimension does not depend on p. It just depends on n and d. And the twist of this object is always equal to 1. So what we will do is to add isomorphism to our category. So we want the object x and x tensor epsilon to be isomorphic. So why do I put epsilon squared here? It's because I want to have an object of dimension 1. So we can do this, and in fact, this is more or less the way we do to obtain a modular category from a degenerate category. So we can do this in a clever way such that we still have a braided pivotal fusion category. And now if we want to understand the number of isomorphism classes of simple objects, we have twice the number we wanted to. But that's nice because remember that when we add this isomorphism, we still have an object in the symmetric center, which is epsilon. So here we have a category and we understand its symmetric center. So if n and d are different modulo 2, here we have 1. So the symmetric center is equivalent to the category of D2 graded vector spaces with the usual dimension. And if n is equal to d modulo 2, so here we have -1, and the category is slightly degenerate. So in both cases, we obtain a modular datum of the size we wanted to, because we only need to choose half of the objects. So here, as before, we have to check that we do not have x and x tensor epsilon isomorphic. But we have a grading on the category, so we can do this easily. And most importantly, we have obtained a categorification of the Z-modular datum. So here I write up to signs because we need to change some signs from the S matrix of this category and this category. So we have to conjugate by a diagonal matrix of signs. But conjugating by a diagonal matrix of signs is exactly changing the signs in the basis of the protonic ring. And using this theorem, we can prove the two conjecture of Kuhn's. So here, these signs say that we have, in the first case, we have found the signs such that changing the signs will make the structure constant non-negative. And here we have to do some more work if n and d are both odd. And for the second conjecture, we only have to take care of the case when n and d are both even, and we have this categorification by a slightly degenerate category, and this will imply the second conjecture of Kuhn's. And just in the last maybe minute, 15 seconds or 30 seconds, I will go back to the Fourier matrix, and here it's quite easy because we have a categorification of each of these matrices. So what we will do to obtain a categorification of this tensor product, we will take the Deligne tensor product of the categories we have constructed. So if we look at this category, so I have a psi inverse just to have the complex conjugate. If we look at this category, it should be a categorification of this matrix. Now we want to have some submatrix, so we'll have to take a subcategory. So it turns out that this category is graded by the cyclic group of order D. And if we take the component of trivial degree, it does the job very well because the symmetric center is tensor generated by the elements, the images of the symmetric center of every tensorand. So we just have to check that each epsilon is indeed in En, so it's true, and there is nothing more. And here we use crucially this hypothesis to add that the symmetric center is not growing when we take a subcategory. So if we have the sum is equal to 0 modulo D, and we take the subcategory, the symmetric center gets bigger. We have another object in the symmetric center. And finally, we have a categorification of the Z-modular datum associated to the family. So thank you for your attention, and I will stop there.
All right, let's please thank our speaker then.
Thank you.
All right, does anyone have any questions for Abel?
I have a question, which is probably just basic, but exactly how do you obtain this D zeta category from your semi-simplification? Like, so what is the construction? Yes.
So you have the simplification of the subcategory of tilting modules. And then we obtain this category by adding some isomorphisms. So this can be understood in another way by a concept called de-equivalentization. So I don't know if you know it. So basically you change the home space between X and Y to be the direct sum of the home space between X and Y tensor epsilon 2, Y tensor epsilon 4, and so on. So basically you just add isomorphism, and you need to check that you still obtain a category, you still the braiding. So if you have a morphism between X and Y in your category Txi, you will have it in Dxi, and so on. And so if you want, when you have a slightly degenerate category, you can do the same thing by adding an odd isomorphism between X and X tensor epsilon to obtain from a slightly degenerate category to obtain a super category, which will be non-degenerate in some sense, because you have killed the symmetric center.
Could we ask you what epsilon is?
Epsilon, it's the generator of the symmetric center. So you have to compute the symmetric center. And
or what is it?
Sorry?
Is it the determinant representation, or what is
No,
it?
it's not the determinant representation. So it's of course it's an invertible object, and so if you look at the representation of UC of SLN, you know that the set of invertible objects is generated by only one object. So you have it corresponds to extremal weight if you want. So you take the difference between lambda1 and lambda n to be maximal. And then you have to twist with the determinant. So if you look at the representation at this fusion category constructed with SLN, you have a bunch of invertible object, and the subcategory of invertible object is of order n or n-1 n, and generated only by one object. So you take this object and you have to twist it with the determinant to have something in the symmetric center. So the construction of epsilon is quite explicit. So it's just a matter of showing that it's in the symmetric center.
So if there were Zirkel bimodules for GD1n, and I'm not saying there aren't, would this category be like the symmetric center of the Drinfeld center of some cell or some J-ring?
So in fact, when I first started working with these, I had another version where I obtained only some of these modular datum, but instead of using the representation theory of UQC of GLN, I used a Drinfeld, the Drinfeld center of SLN, of UQ of SLN, because I had in mind that this category should be the symmetric center, the Drinfeld center of some category. Because we hope that if Zirkel bimodules exist, we hope that this category, a categorification of these data should be given by the Drinfeld center of these Zirkel bimodules restricted to a two-sided cell and truncated with some, and the tensor product which is truncated. So I'm not quite sure that this category will be equivalent.
How many different fusion categories can categorify the same modular data? Probably the simplest.
How many? I don't know. So sometimes you can have many different categories. And something that I'm interested in is that if you take the Drinfeld center, you have a lot of categories which have isomorphic Drinfeld center. So it's quite difficult to understand if we still have in mind that we should have Zirkel bimodule somewhere, we should have these cellular categories. And taking the symmetric center of these cellular categories, we should have a categorification of these modules. So here, sadly, I do not have, this category is not realized as the center of some other category. But this is the hope that there is a categorical story happening here.
All right, we should talk.
All right, I'm going to stop the recording. And of course, any questions are welcome to continue. But let's thank Abel once again. Thanks so much.